I'm going to go get started with a few. All right, good morning, everyone. So I'm going to be projecting from my iPad so that I can see what's going on online, just in case there's any interruptions. But just know that I'm recording this. Also, the lecture has been pre-recorded from last year, just in case there's any interruptions that occur. So just to review with everyone, everything that we have in terms of presentations will be available online on the website. So these lectures, I do tend to update them. So just be aware of that. They are available right now online, but just note that I will update them. You'll see the date that they've been updated. There are also, as you can see from the syllabus, things that are arranged in a certain order for this particular semester as it relates to the project that we'll all be working on. And that's something that I will separate a certain time for us to need to discuss the details of how we're going to go about doing this project. Another thing is that I've already also posted your first assignment located on the website. Any doubts you have with regards to it, just let me know so that we can address it. That's going to be due in a couple of weeks. And that has to do with some of the material that we discussed in the first lecture. All right. So what we're going to do today is kind of bring everyone on the equal ground for the fundamentals that we're going to need in order to be able to dig deeply in the literature that we're going to use as part of this course. So this will be reviewed for several of you, which is fine. And this will be probably new for some of you. That's okay, right? But we want to be able to get ourselves to the common language. How can we discuss the chemistry that is important for metals? So I've entitled this the fundamental bioinorganic chemistry. And so let's start off where the field of metals in terms of their appreciation chemistry began. So this has to do with coordination chemistry. But historically, that began with the contribution to Alfred Werner in the late 19th century, who began to formalize this particular field. And so this has to do with understanding what are coordination compounds. And so today, that's something that we can appreciate in terms of the structure that we are more commonly familiar with. But at that time, that concept of how metals can be part of a compound and what type of bonds they can form is not very clear. All right, so what we're looking at here is what is coordination compound? So that has to do with composition of bonding interactions between metal atoms or ions. So I specify that because we're talking about metals that can be in neutral form or they're going to be in their charge form, the positive charge form. And so here we're going to be more specific about transition metals. That's going to be mostly the focus of the course, but we will dive a little bit into some of the main group metals. And as part of that bonding interaction is the interaction between metals and ligands, one or more ligands. So what exactly is carbon? Carbon. What is a ligand? Go ahead.
Ligands are typically the molecule or compound that coordinates directly to the metal center. Any sort of atom generally can coordinate, but often it's a nitrogen or carbon that's coordinated.
Okay. So Carmen basically nailed it, except that she said molecules. And so it doesn't necessarily have to be molecules. It can actually just be individual atoms that can serve as an interaction with a metal. But when we're talking specifically about coordination compounds, their molecules probably take a much more important role. So we'll discuss that in a moment. All right, so let's focus on this very simple reaction, right? So this is a chemistry course. So some reactions that give us a fact. Here, we're looking at a metal. As it interacts with a letter L, that letter L is a representative of a ligand. All right, so what we're focusing on here is this pair of electrons, because the ligand is providing electrons to the metal. So what we're showing here is the movement of those electrons to the metal and forming a metal ligand atom or metal ligand bond. Right, so that's basically what underlines the coordination compound. But let's look at this a little bit more deeply. Now, when we're talking about specific theories that help us to understand these type of compounds, here we're focusing on a type of acid-base theory known as the Lewis acid-base theory. Have we all heard of Lewis acid-base theory? All right, so this is something crucial to understanding this interaction. So we have this Lewis acid, which in this case, the metal is the Lewis acid, and then we have the ligand, which is the Lewis base. They come together to form this metal ligand bond. All right, so when we're reviewing Lewis acid base theory, acids are those things that are electron pair acceptors, while the base is something that's an electron pair donor. So based on this definition, the Lewis acid base theory is quite encompassing of a lot of different species and interactions. When it comes to coordination chemistry, the metals, as I already mentioned, are the Lewis acids, and the ligands are the Lewis bases. So just expanding on the definition that Carmen gave us, the incorporation of atoms, ions, or molecules that can donate the electrons to the metal center. All right, so here we have this representation. Now we're a little bit more specific here. We have silver in its cationic form interacting with ammonia molecule that when it coordinates to silver, or when it coordinates with any metal, that particular molecule is referred to as amine. Okay, so here we see two of these ammonia molecules, the amine ligands, coordinated, and you're forming this structure here, where you have an actual two bonds to the nitrogen from the given ammonia molecule, giving you this linear structure. We're going to discuss this idea of coordination number, because here the coordination number is what, everyone? 2. We're going to discuss this idea of coordination number as it relates to geometry for the moment. All right, so again, the movement of electron pairs coming from the amine, and then we have a special type of bond occurring here. And why is this a special type of bond? Well, probably the majority of us no longer special, but the thing is that we normally think about bonds as sharing electrons between both species, so both species are contributing. But in this context, the pair of electrons came from the ligand, right? So this is known as a dative bond, electron pair coming from the Lewis base. Now, I will say that this definition of a coordination compound is simplistic because it's implying that always a metal-ligand interaction has to come from electrons being given by a ligand. But the reality is that the metals have the capacity, very metal, to donate electrons in the actual bonding interaction. All right, so the dative bond is what is referred to as a coordinate covalent. All right, so what do I mean by coordinate covalent? Well, that implies that we have properties that are mixed of covalency, sharing of electrons, and ionicity, that is the distribution of charge. All right, so let's look at certain ligand properties. And so here I'm providing you with a table of ligands in terms that are more commonly found, but obviously this is super simplification. There are many things that can show this. What I have listed here are those ligands that we can refer to as being neutral in charge. And so here I'm showing you the collection, a brief collection of amine ligands, right? So we have a representation of the nitrogen base ligands that coordinate through their free pair of electrons on the actual nitrogen. So we're referring to these electrons here. And the other column, again, neutral ligands, where we're showing water as an actual ligand, okay? And that's actually really important in our understanding of metals going into water. And why is that important? Because in the biological context, solvent is water is going to be our main solvent. So we have these other ligands that are also neutral. And then here, just giving you one example of a type of ligand that is phosphorus-based, very similar to the amines, but these are representation of the phosphorus. All right. So what about ligands in terms of their charge state? Well, when we're thinking about that, then typically ligands are going to be anionic. And the reason for that, again, source of electrons for metals. So the more electrons there are, the possible interactions that they're capable of. So here we have representations of anionic ligands. We have our list of halides that can serve as ligands. Those ligands that are referred to as the pseudohalides, although they're obviously not halides, but they have similar types of properties, and the ones who form the category of others. So I'm not going to go into any depth right now in terms of any of this, but I want to mention that typically you're going to find ligands either neutral or anionic form. Right? But there are some examples of ligands that are cationic, right? And so not as common. Why would that not be as common? Okay, what do you think? Exactly. So we usually have metals in their cationic form. That's what Javier said. And so the idea of something positively charged interacting with positively charged, you tend to think of this electrostatic repulsion. But there is a capability of some types of ligands that are cationic that can facilitate this type of interaction. All right. So as part of this description of ligands then, so we mentioned this idea of charge, right? There's also this concept of density. All right, so the root of that word is dense, right? So you think about dense, we're talking about dental, talking about teeth, this idea of ligands being able to bind onto a metal and form this coordination. So denticity, that's the capability of ligands being able to coordinate through their atoms at different sites on the metal. And so that can help us to define the number of atoms at which that ligand can bind to the metal. So let's look at an example. Here we're focusing on water, which in terms of its de novo case, refer it as a ligand is an aqua ligand. And so what do we observe? We observe two free pair of electrons. Okay? They have the capability of forming a coordinate covalent bond with a metal. And so here we have that representation where you have that coordination with the metal through the oxygen. And so if we're going to define this denticity, right, is only binding at one site through the oxygen. So this would be referred to as being something that is monodentate, right? So we'll use a prefix, in this case mono, and then the term dentate to define how that ligand is coordinated to that particular metal. All right, so one thing to note, although that's something that's, again, oversimplification, coordination typically at the most electronegative atom. So when you want to get a sense of where is this going to occur. All right, so we use these prefixes to define denticity. So we're going to look at a table that helps us to appreciate this. All right, so here's our list of prefixes and what they imply in terms of the coordinating atom. So mono, 1, example we just saw with the alpha ligand, 5, 2, coordinating atom, 5, 3, extra 4, and so forth. You go on this. All right, so visually, how can we represent this? So what I like to use is a structure like this. So this structure may not be so obvious to everyone, so I'm going to just review it before we go into anything. This particular structure is one that corresponds to a coordination number 6. So again, I mentioned to you, but I will go a little bit more in depth in a moment, that there's a correlation between coordination number and an ideal geometry. Well, the coordination number 6, what we have is what is referred to as an octahedral geometry. Okay, so what does that actually mean in structure? What that means is that we have six different atoms that are surrounding that metal center. We have our metal here, okay, and so what we're going to define is the positioning. It's already drawn there, but I want to elaborate on what I have drawn there. Sometimes people don't understand some of the way that actually drawing is represented. So according to this, we have two types of positions in which atoms can be located. We have two positions that are in the plane of the screen. You see this plane of the screen, where you have, I'm going to put, again, use the general term X as an atom coordinating metal. So this is linear, and it's right on the plane of the screen of my actual iPad here, of the computer screen, wherever anyone's sitting looking from online. All right, but then we have this other position. This other position where the other 4 atoms are coordinated, and that's going to be on a plane. And this plane is actually perpendicular to the screen, right? So just imagine perpendicular, what we see here. And so the way we have to try to draw something 3-dimensionally, even though we have structure that is 2-dimensional, is by trying to just emphasize it by using wedges. So I use these wedges like this to emphasize something that's going behind the screen, so behind my iPad, behind the screen here. Okay, and then I use this type of drawing here to imply that I have something that's actually coming in front of the screen. Okay, it's at 90 degrees. So this implies that we have something that's perpendicular. So now we're going to put those 4 remaining atoms, as so, and that gives us then those particular atoms in a position referred to as equatorial. So this would be equatorial, okay? And then those other 2 atoms that are on the plane of the screen, that's the position that's called axial, okay? So we're going to review this in a moment, but I wanted to emphasize so that this doesn't appear as something random. So we're going to then focus on this idea of all right, so in this context then, we're using a certain letter to represent coordination to the metal center. So A is our ligand, and it only has 1 atom. So here we have the representation of something that's monodentate. All right, we saw that kind of example. Right? Now using 2 atoms coordinating to the metal center, and I'm showing you this symbol here because I'm trying to keep this in a generic fashion. There's a bridge there, and it forms a ring when it coordinates to the metal center. When this happens, we have something that is bidentate. Then you have over here a representation of three atoms that are linked in a molecule that are going to be tridentate. And then here you have the corresponding tetradentate, pentadentate, or again focusing on the actual prefix, and then you finally have something that is hexadentate, right? Just to give us a perspective of what does that mean to fulfill that density. And we'll note something very important. Just because a ligand has the capability of a certain type of denticity doesn't mean that it actually will always use all of the coordinating sites, right? That's something that's very crucial, especially when we're talking about the stability of compounds in solution. There could be some what is referred to as partial stability or partial dissociation because of this particular feature. All right. So when we're referring to a ligand that has that can bind at two or more sites, well, that's something that is polydentate, and we would commonly refer to it as a chelator. Right? So probably you've heard of the term chelation therapy. We're coming from this idea of a molecule that can bind a metal in this modality. All right, so this refers to another type of interaction between metals and ligands. So this is related to denticity, but it has this distinction. We'll clarify that. So when we're referring to hapticity, that is the coordination of a ligand to a metal center via an uninterrupted and contiguous series of atoms, right? So that's different from the denticity principle, where it can be coming from any part of the molecule. Here, it's going to be actually connected, right? So when we're referring to hapticity, we actually use the symbol eta to emphasize it, right? So look at it as an example. So here is a classical ligand, this cyclopentadienyl anion, which actually is not stable in its monomeric form. Okay? You normally would find it in a dimeric form. If you ever want to do synthesis, you extract that molecule to get at the monomer to then able to explore its coordination. All right, so in this representation, where we have it as a monomer, as you can see, you have it as an anionic species, right? And we have 3 important electron pairs here. Right, so these 3 important electron pairs are the 3 electron pairs here, and then the ones that are supplying the double bonds. Okay, that's going to be really important because these have the capability of facilitating metal binding, and that's going to be important for us to understand the type of structures that it can form and why this particular ligand can give us a different toxicity. So let's show you the representation of that. Right here we have representation of a 1 contact with carbon in that metal. Over here, we have a contact with 3 carbons, the contiguous to that metal. And then over here, we have 5 contacts between carbons and metal. So here we're giving a representation of something that we would classify as organometallic. Okay, organometallic. Why do you think that is? Oscar, why is this organometallic? Why is this organometallic? Okay, it's a little bit more specific than that. It implies that you have a metal-carbon bond. It's a really important feature. All right, so in terms of our representation, eta-1 for the example to the left, eta-3 for the example we have a 3 carbon contact, and eta-5 for the example of 5 carbon. All right, so then here, we can think a little bit about coordination number, right? We talked about this idea of a bond and how it represents a number. So you would think eta-1 would imply coordination number 1, eta-3 implies coordination number 3, eta-5 implies coordination number 5. But it gets a little bit complex, especially when we start to talk about structure. So eta-5 especially is a little bit difficult to really define super well. Because by the eta-5, we have that 5 carbon ring that's interacting with another center. Right? And so you would think then that coordination will be coordination number 5. But then if you're talking about the electron pairs, because that's something we define as fundamental to metal-ligand interaction, well, that's fundamentally then 3 electron pairs that are basically resonating through those 5 carbons, right? So then there you would think, well, maybe that's a coordination number 3. But it also then gets more complicated when we see certain structures, like this particular structure that has a titanium center. This compound is referred to as titanium dichloride. We have 2 of those cyclopentadienyl rings coordinated to the titanium, and you have 2 chloroligands. Okay, so then here, how do we define this coordination number? Well, as we're gonna get to in a moment, we have a certain geometry here. So I haven't defined it yet, but Carmen, what is the geometry? Okay, so Carmen says for a planar. Jaylene, what kind of geometry? Okay, give it a shot. Or you can say, I don't know. That's fine. All right. You don't know. Javier? Tetrahedral. Okay, so Javier gets the point there. This is tetrahedral, right? So tetrahedral, we think back all the way to those days of organic chemistry, right? And so we have four atoms that are connected, well, at least back in organic chemistry, that was carbon, right? And so we have a certain sense of the four contacts. So you would think then for tetrahedral, then, well, that should be then coordination 4. So what is it? The coordination 8, coordination 12, 4. So that's something that's still a bit not necessarily nailed down. How you exclusively define this. So I would say in this context, it's probably stick more to this idea of correlation between geometry and the coordination, right? So let's review that. All right, so then this idea, coordination number and how it can help to give us a sense of what a geometry is. And so here then, coordination compounds adopt highly organized structure and depending on the nature of the ligand, predictable geometry. So I want to say that this is, like many things, a bit of a simplification, but we're going to go with this to help us to get a beginning insight into structure. Coordination number dictates idealized geometry. So if we have one coordination, right, well, that's kind of a, not so complicated. Obviously, there's going to be one interaction, so we really don't define much there in terms of geometry. Once you start getting 2 or higher, that's where geometry really plays a factor. So you have the linear geometry, like the example of the silver with the 2 amine ligands. What do we have there? We have this particular geometry where you have the ligand, metal ligand, bond angle, what? What's that bond angle? 180, perfect. Okay. Then we have a coordination number 3, where we have a trigonal structure. So you draw something that's trigonal, and now you have those ligands that are coordinated to the metal, and so you're going to have a common ligand-metal ligand bond of 120 degrees. Okay. And so then we move forward. And here we start to get a little bit more complex, where this is the source of Carmen's mistake. Coordination number 4 can actually have 2 different types of structures. You can have tetrahedral, which was what was titanium dichloride, and then the tetrahedral model. And that's what I mean by how I use these wedges. So here, these 2 ligands and the bonds that I've drawn there are to imply that that's on the plane of our screen, my iPad, what we see on the board. But the way I've drawn these particular bonds, one is behind the screen, one is in front of, and they're actually going to be perpendicular to the screen. And then in terms of our bond angles, what we're looking at here are classical 109.5 degrees. Okay. But then the other geometry, that's what Carmen had mentioned, square planar. But here, the way I'm drawing this is with the 4 bonds on the plane of the screen. But I will mention to you that in the literature, you may not always see it like this. You might see it more like this, which is probably also why you said what you said. You probably will see it like this. Okay, and so that is also square planar, but from our perspective, that is actually perpendicular to our screen. Okay, and so that will still retain this idea of bond angle of 90 degrees. This is also 90 degrees here. Ligand metal ligand. Okay. All right, so now we move on to coordination number 5. Coordination number 5 also has 2 idealized geometries. One is the trigonal bipyramidal structure, right? So I'm going to draw it here. So here, as we already alluded to with the octahedral structure, we actually have 2 different positionings where the ligands can be. We have a positioning which is the axial, and so that's here. This ligand and this ligand are in the axial position. So these are lying on the plane of our screen. And then we have 3 ligands that are in the position that's equatorial. So they're going to be on a plane that's going to be equatorial or to perpendicular to what our screen is. Okay, so we have this ligand, and this ligand, which are part of the equatorial plane. All right, so because of these 2 different positionings, right, then we have corresponding bond angles. So here we have a little bit more complex. What we have from the perspective, okay, of a ligand in the axial position to a ligand in an equatorial plane, that ligand metal ligand bond angle is 90 degrees. If you were to go from ligand active position to the ligand in the other active position, that ligand metal ligand is 180 degrees. Then if you look at ligands that are in the equatorial plane, okay, ligand metal ligand bond angle of 120 degrees. Okay? Well, then we have another structure, which is a square pyramidal structure. So here we have, again, two different positionings. One in which we have a ligand that's in an active position, and one in which we have ligands that are in an equatorial plane that's going to be perpendicular to the active position or perpendicular to our perspective, which is the screen right here. Okay? And so here we also have corresponding angles where you have ligand of axial versus ligand of equatorial, ligand metal ligand bond angle of 90 degrees. And the ligands that are in the equatorial plane, ligand metal ligand bond angle of 90. All right, just to give us a perspective there. Now we go to coordination number 6, which we have already discussed to an extent. So we're ready to find that we have the active position, we have an equatorial position, or plane where the ligands are located, and then we have corresponding bond angles, right? As we define from the active to the equatorial, and then ligands in the equatorial plane, what angles we have. Okay. The reality is that you're not going to always have these ideal geometries, because you're going to have different types of atoms coordinating to the metal center, and then if you're looking within a biological context, you're going to have a lot of distortion in terms of the ability of an atom to coordinate to a metal. So that's going to give you a lot of deviation. But for us to be able to appreciate the fundamental interaction between metal and ligand, we need a little bit of theory to help us there. So we're going to dig back into the Lewis acid-base theory for us to understand this idea of a preference. Okay, what do I mean by preference? This idea of what's going to underlie a metal-ligand interaction? What's going to draw them together? So here we're going to look at a subset of the Lewis acid-base concept, which is the hard, soft acid-base theory, or commonly referred to as HFAB. We see this a lot in the literature. So what we're looking at here is something that stems from the 1968 Pearson and Chat, and it has to do with this recognition of species and their polarizability. Right? What do I mean by polarizability? Javier. Polarizability. Well, polar. Cuando decimos, exactly. So polar, you're referring to charge, right? And so here you're thinking about whether or not you have a localized cloud of electrons, right? Localized, or is it actually going to be pretty broad? That's what polarizability means, right? Do that. All right. So with that in mind, and so anyone that's online, you can feel free to ask questions. Don't feel like that you can interrupt. So if I'm going too fast, just let me know. All right. So polarizability, this idea of this electron cloud, right? Of this localization of charge. Well, they wanted to explore this because they saw that there was a correlation between the polarizability and the preference of species interacting with one another. So let's look at this concept. We're going to look at a random base and its interaction between something that is a non-polarizable and polarizable Lewis acid. So here we're looking at a random base, and I'm representing that as the letter B, okay, with this corresponding electron pair. And I'm focusing on the Lewis acid P. I'm focusing on the proton. Very simple. The proton we know is small, and we know that it's going to be quite localized, right? So that's going to be non-polarizable. So here we're going to do this sort of affinity, relative affinity, where we're looking at the binding of the base to the proton and measuring that K value, that equilibrium, but really that attraction. Okay. So then we're comparing that to something that is a Lewis acid that is polarizing. So here we're focusing on mercury, methyl mercury, and how it interacts with, again, a given base. And so our comparison is going to be the affinity of that random base to the non-polarizable proton and to the polarizable methyl mercury. And so what they use, so they set up these affinity scales, and so they basically start to define preference based on which one has a stronger affinity for the proton or which one has a stronger affinity for the methyl mercury. All right, and with that, they put categories. So if the affinity K to the proton is much, much higher than to the methyl mercury, then that base is referred to as being hard. And so something that's hard will be something that's non-polarizable, and as part of that, high charge and charge to size ratio. And so these are factors that are going to be something that is implicit with the definition of the category hard. But if the affinity to the methylmercury is much, much higher than the proton, then in that species, in that case, the base would be soft. So basically, anything is considered soft if it's polarizable and has a low charge to size ratio. All right. So then, well, that's just something based on the affinity profile. But how do we look and try to define this much further? Then we have the third category, where your affinity to goals are going to be comparable. And so when you're in that category, you're going to be something that's called intermediate or border. Okay, so you have all three categories. But how do we go about trying to define something that's hard, something that's intermediate, something that's soft, and then acid and base? All right. So we need to refer to a periodic table, and as you know, none of our rooms have periodic tables, so we have to bring one with us. All right, so we have this periodic table here. So the first thing I'm going to ask is where in the periodic table are you going to find something that is an acid, and where in the periodic table are you going to find something that is base? Let's start there. Carmen, where should we find acids and base? So that's the acid base. So what about base? All right. So generally, you're good with the bases. So what we want to think about is this idea of being able to collect electrons and those things that can give electrons. So we have to think all the way back to general chemistry part, where we talk about those things that have the capacity to give up electrons, those things that have capacity that have a really high attraction to electrons. So in that context, then, what is something that can become cation? Well, in that category, every metal has a capacity of becoming cationic, and we throw in the proton in there. So the majority of this periodic table is going to be things that have the capability, let me throw that part up anyway, have the capability of being acid. Okay? But then all the way to the right is where we find the category of things that are going to be base, things that are capable of becoming anionic. All right? So that's the general properties that we can pull from our younger education. But then how do we start thinking about things in terms of hard and soft? So then we start pulling from other properties. For instance, that the size of the elements get bigger as we go from the top to the bottom, okay, in the periodic table, and also how it decreases as we go from left to right. Because remember, one of the implicit properties is charge to size ratio. So you can then get a sense of where are you going to find these things based on the size, right, and the capability of being able to become cationic or anionic. All right, so let's clear this up a little bit so we can see this. So we have then, based on size, right, the smaller the size and the higher the charge is, the higher the hardness is. But then, when you think about electronegativity as another component, okay, electronegativity, the higher the electronegativity, the higher the electron localization also implies the higher hardness, right? So these are different components that we need to think about, but it still doesn't make it easy for us. It's not as if with all of this information we can immediately point to where you're going to find something hard, intermediate, or soft. So I point to this other periodic table that's going to help us. Well, when first you list this, then it's really well, generally speaking, those things that are going to be hard acids will be, for instance, protons. I already mentioned that to you. But also, we have the first column, which would be the alkali metals. Those are classically hard, having the alkaline earth metals, which are also classically considered hard. And then you have a sprinkling of transition metals that are in the first row that would typically be considered hard acids. But I'm going to put that with a little bit of a star because it's not always the exact. Because we have to refer to the charge, where in the high oxidation states is where you see them as a hard acid. Versus soft acid. For soft acids, where you typically are going to find those in the latter part of the periodic table, okay? And typically with the emphasis on a low oxidation state. Okay? Again, the charge to size ratio is going to be important. All right, so here is a periodic table that gives us a better understanding of where we can pinpoint. So here, as I was mentioning to you, part of the periodic table where you're going to have your acids. So to your left, that's the majority of those things, the things that are going to be your acids. And then to your right, the things that have the capability of being your base. Then we break it down into hard and soft. where, as I already mentioned to you, where we see the classical alkaline earth as being hard, and we have a number of these transition metals that are hard, especially as they have a high oxidation state, okay? And then those things that are borderline. So something like iron, for instance, iron falls in both categories, hard and intermediate, because of its oxidation state. So you can see over here, iron 3 plus is hard versus iron 2 plus being something that is sort of borderline or intermediate. And then over here, those things that are soft, having to do with, based on the polarizability of the species. So this gives us a better perspective of how we can pinpoint what's going to be one of these categories. So let's look at it a little bit more in depth. So I already mentioned to you about this idea of the metal, okay? But let's talk about the ligand. Well, when you have resonance can affect the hardness of a ligand, whereas oxygen is an example of a Lewis base, right? We have capable of binding a metal that is considered hard. But if you resonate the electron pairs, right, through the molecule, that's going to decrease the relative hardness of each individual oxygen, right? So it makes it a little bit less hard. It doesn't say that it's no longer hard. If you compare that, let's say, with something that's corollary, like an alcohol, where you have those electrons that they're going to be localized on the oxygen there. Now, if you were to compare the ligand on the left, it's not as simple as saying that we have the individual oxygen in terms of their hardness, because we can also consider the factor of that ligand on the left with the carboxylic acid base, right? It has a bidentate capability. With a bidentate capability that can influence the stability with metal binding. And we'll talk about that a little bit later. And then to re-emphasize this idea of, even for transition metals, their oxidation state can really affect their hardness, and that'll really affect the type of chemistry that they can explore. So that's why something like iron, which is something that we depend on, an essential metal, is highly used because it has that ability to be redox active and to go into different oxidation states and facilitate certain types of chemistry. So that's something that really enables a lot of types of interaction. And we're giving you the perspective of the change in oxidation state as it corresponds to the change in radius as it depends on the coordination number. All right. So we talked about this idea of polarizability, okay, and this idea of hard, soft, and intermediate. So let's put this then into binding preferences principle, where we have the principle that hard acids prefer binding to hard bases. We have intermediate acids prefer binding to intermediate bases, and then we have soft acids that are preferred to bind to soft bases. Okay, so that's going to be fundamental to the type of affinity that you're going to see. It doesn't mean that you're not going to have interactions between something that's hard and soft. It's just that the likelihood is going to be lower, and in certain cases, it may not actually happen at all. All right, so we're going to use this theory to understand some of the common ways metals bind to biological species, right? So you're going to see a lot of this in the papers that you're going to read in terms of understanding some of the compounds that are made, but some of these compounds are going to interact in the body. All right, so let's break this down into the categories of interaction with protein, okay? And so with proteins, we're talking about these compounds that are made up from amino acids. Okay? So let's remind ourselves. I think everyone here has taken biochemistry. What is an amino acid? The basic structure of an amino acid. Awesome. So you're going really, really basic. What is an amino acid? Javier. Good. I like that. So we have something like this. Didn't mean to do that, but we did. Just trying to get back to it, but I'll show you from there. All right, so let's start again. All right, so we have then the groups. We have the proton, we have the amino group, we're going to have the carboxylase, and then we have the arginine. Okay, so this is a typical amino acid, right? And so you have the configuration of it. There's something that's going to be chiral. So the typical features: the amino group, the carboxylic group, the proton, but what distinguishes them is the R group. And so in the human body, we have 20 common amino acids. In biochemistry, you categorize them in terms of whether they're neutral, whether they're acidic, basic, whether they are aromatic, and so forth. All the different features. So proteins are polymers of amino acids. And so you go from the amino acid to the peptides, which are basically the amide bond that forms between the two amino acids, and then it goes to more extensive structure. Right? So I just wanted to reiterate that point because what I want to emphasize first is the sites of coordination, even at the level of the amino acid, because that helps us to appreciate where metals can bind. And so it turns out that metals can coordinate to amino groups in the amino acids. They can coordinate to the oxygen of the carboxylate. Okay, so that's why I have a little star there. But also they can coordinate to the R group. Okay, so depending on what atoms are accessible in the R group. All right, so let's look at that. Well, what type of amino acids R groups do we really have? So we have a number of them. On the top row, there are the aliphatic groups. We have those that have OH groups, like the serine, the cysteine, which have an FH group, so those have metal binding capability. We have threonine that has an OH group, and we have methionine that also has a sulfur group, but also has metal binding capability. Over here we have the tyrosine that has metal binding capability, with the OH group. We have a histidine. We have lysine, which has a amino group there. The carboxylate containing group, aspartic acid, and gluconic acid. Okay, so all these have metal binding capability on top of the amino groups from all the amino acids and the carboxylic acids in all the groups and all the amino acids. And so another thing you see here is my labeling here. I have these labels of H, I, and back here at S. So that's my labeling of whether they're hard, soft, or intermediate. So we have a sense there based on what has metal binding capability, the capacity to bind metals and what type of metal. And that has to do again with the categorization of hard, soft, or even intermediate. Another really important thing is that depending on the type of coordination, you might have different modalities of coordination. So what do I mean by modality? Well, it has to do with the capability of binding at more than one site, okay, or at different sites. So in the example we have up here, I have the example of the carboxylic acid group. It has the capability of binding in a monodentate modality, so that's monodentate, versus binding in a bidentate modality. Okay, so it's going to depend. So probably as an individual molecule, maybe it would just be something that is capable of bidentate. So let's say that if you were in a protein structure, depending on space, that might depend on whether it be monodentate or bidentate. Something we see when we look at histidine. Histidine has two nitrogen groups that both are capable of binding metal. Okay, so I'm not going to say that there's a higher preference for one or the other. And typically, especially in a protein structure, depends on the spatial arrangement that the metal can. Just point that out. All right, so here's just further features of how metals can coordinate to different amino acids and the different groups. So we have coordination to the nitrogen here, coordination to the sulfur, coordination to the oxygen. Just to give us perspective of the coordination of that. All right, so that was from the level of just amino acids. That's the monomer of the protein. So let's go a little bit further than that. So going from amino acids to peptides, so I already gave you a brief definition. And that is that you're forming between two amino acids an amide bond. All right, how does that happen? Well, you have the carboxylic acid of one amino acid interacting with the amino group of the other carboxylic acid. And that leads to a release of water. So that's something we have explored in biochemistry. So here then, we're looking at the perspective of a peptide. So basically it's a string of amino acids. And peptides typically don't have a defined structure, where proteins tend to have really well-defined structure. That's generally true. There are some examples of peptides that do have some degree of structure. That's not to say that they don't ever. All right, but going back to the idea of binding, when we're looking at this thing, we have now a definition of where we are located along the sequence. Okay, sequence means the arrangement of the amino acids. So on the left side over here, we have the side that's called the N-terminus. Right? That's where our free amino group is. On the right side, we have what is referred to as the C terminus. that is where we have the free carboxylic acid. We don't have these free amino groups of carboxylic acid anywhere else because we always have those amides that are linking the amino. So at the end, they have capability of binding metal. And it's actually important because if you think about copper and copper, how it gets distributed in our blood, well, the protein albumin uses its amino end to coordinate copper, and it plays a really important role of transporting that metal into our cells. So that's never to neglect the end because they can play a really important role. But then in the actual sequence, we see how the amines lend themselves to additional binding sites in addition to the actual R groups themselves. So that's what I want to emphasize, how the peptide backbone, the actual amine, facilitate additional binding. So here we have the amine bond that exists, and how the metal can bind to the nitrogen, or it can even bind to the oxygen. That's not to neglect that possibility. So that facilitates additional layers of how metal can bind to a protein. All right, so that's just the fundamental perspective of metals and where they can bind to the actual protein. So let's give an example. Let's look at an example of zinc, okay, zinc 2+. All right, so from our perspective, zinc is it hard, is it intermediate, or is it soft? What do you think? That's correct. Zinc is falls in the category of something that is intermediate. Okay? So right there. So zinc 2+, intermediate. You have to earn that. But yeah, you earned that point. Move over here. Sometimes my fingers. All right. All right. So zinc is an intermediate metal, so it tends to bind to things that have more of an intermediate property, but that doesn't mean that it doesn't have the capability of binding to something that's harder or softer. As an intermediate, it has that flexibility, right? All right. So in our cells, we have family proteins called the metallothionein. So these are really important proteins because they participate in the storage of that metal. Okay. So as it turns out, essential metals that our body depends on, we have the capability of storing them. Metallothionein participates in that for zinc and also for copper. So we're looking at here, these are proteins that are low molecular proteins and they're quite concentrated. There's about 2 millimolar in the mammalian cell. So 2 millimolar may not seem like it's high, but it's actually quite a high concentration, especially for proteins. So these consist of 61 to 62 amino acids, of which 1/3 of them are cysteine containing. Right? So cysteine is a sulfur, is a sulfur site that facilitates coordination to the metal. So let's look at this perspective here. Again, this particular family of proteins that will coordinate the zinc 2+ and also provide coordination for copper 1, copper 2. So to the right, we're looking at a picture that displays where those cysteines are located. Okay, and it also displays that there are 2 domains. There is an alpha domain and there's a beta domain. The alpha domain contains 4 zinc, okay, and the beta domain contains 3 zinc. All right, so let's look at the coordination of the zinc. Okay, let's focus on this one right here. So that's probably an easier one to see. All right, so Javier, what would you define that coordination geometry as? Or at least first, the coordination number. Yeah, that zinc right there. Coordination number 4 is that tetrahedral spur plane. And so it turns out all these things, in terms of their coordination, are actually going to be tetrahedral in nature. And they're coordinating to sulfurs, where you see some of the sulfurs are actually serving as bridges between 2 different things. So you can see this example right here of a sulfur that's bridging between the 2 things. Right? So then we can see how this particular small protein, so it's relatively small, still can facilitate a lot of metal binding. And back to the protein with extensive metal binding serves as a storage thing. So it houses the things that are going to be needed if any kind of decomposition do not change the world. All right, so let's switch from protein to then nucleic acid. So just like we established for protein, we look at the building blocks. So we're going to start from nucleotides, okay? And a nucleotide will be our monomeric form. They're the building blocks of nucleic acid. Now let's look at the classical features of an actual nucleotide, where we have the base, where we have the sugar, and then we have the phosphate group. All right, so we have, in this case, the base is the adenine base here. The sugar is the deoxyribonucleic sugar, so it's going to be very important. It's what forms part of the DNA structure, and then we have the phosphate group. Okay, so that's going to be our building blocks here. All right, so when we then look at it from the perspective of the different types of nucleotides, here you have adenine, you have cytosine, guanine, thymine, and then here is uracil. All right, the difference being that that one participates, this particular nucleotide participates in the structure of RNA. All right, so just to give us that perspective, where we have the same fundamental groups, what's the difference is the actual base that's part of these nucleotides. All right, so what links our monomers? Essentially, what we see is this formation of a phosphodiester bond that occurs between the phosphate group of one of the nucleotides and the OH group of one of the other nucleotides, facilitates the formation of this phosphodiester bond. We can see it more clearly here from this perspective right here, how we have that formation occurring. Okay? And so now we have the sequence. So we're looking at the sequence from here down, where we're looking at a free phosphate group on one side, and then over here we have a free OH group. Okay? So that's the two ends, one with the free phosphate, one with the free OH group. But in between, in that sequence, you're not going to have those three groups because those are what's participating in the phosphodiester bond. All right, another really classical feature of the nucleotides are what occurs at the bases, where these bases, you see these arrows here. So in biochemistry, those are the sites where hydrogen bonding occurs. And those hydrogen bonding is actually really important in terms of the structure that DNA can possess and stability that's supported in these molecules. All right, so we typically read it from 5' to the 3' end. Similar to what I mentioned to you with protein, how we look at it from the N-terminus to C-terminus. That's how we typically read protein. So in this case, of nucleotides, how we usually read it. All right, so just to emphasize, phosphate group at the 5' end, and then we have a link that are the phosphodiester bonds, and then the hydrogen bonds that can lead to the classical types of bonding interaction between nucleotides. All right, so let's look at this a little bit more closely, where here we're looking at the actual hydrogen bonds that occur between the typical partners. So in this case, we have the hydrogen bonds that occur between the adenine and thymine. So we have here the two types of hydrogen bonds that are occurring. And then you have for the two G and the C, we have the classical three types of hydrogen bonds that can occur. That's not the only type of hydrogen bond that they're capable of. So these are the ones that facilitate the typical structure that we see for DNA. All right, but more extensively, one type of structure for DNA is the B structure, beta structure here, where we have this classical coil arrangement where you have the bases arranged in sort of base layers. We have then these grooves that are formed from the what is referred to as the minor groove, or what's referred to as the major groove. Okay, so we have then this orientation of how the bases interact with one another, and then the exterior, or the backbone of this, is where you find the phosphate. Okay, so here I want to emphasize this because it gives us a perspective of how complex this can be, okay, and the where metals might have the capability of interaction. One other thing I want to show you here is this arrangement. So you can see here, we have this base parent, and you have the 5' end, the 3' end, the 1, and then the pair with another sequence, 5' end, 3' end. All right, but where in this structure, where we would expect to see metal binding? Well, we would typically expect to see metal binding at the nitrogen of the bases, at prime sites. Nitrogen is typically something that would, depending on where it's positioned in the molecule, it can range from being hard or intermediate. Okay. We also have the phosphate, the free phosphate group that definitely has metal binding capability. And then also we have the phosphodiester backbone that have metal binding capability, right? So you have different sites that are capable. If you look at it as a primary sequence, but obviously DNA is much more complex than that. So look at it a little bit more of a realistic representation. Again, still a cartoon, but just to give us a perspective of coordination. Well, you have some metals that can facilitate, if you look at it from the perspective of the actual strand, right? You have, this is one strand here, 5' and 3' that's interacting with another strand here. And what we see is that we have a coordination represented by this red dot right here that's forming a bond between the actual two bases, giving us what is referred to as an intra-strand cross-link. Okay? So in the same strand, you have that metal that's coordinating with two bases, and it results in this type of structure. Another thing that's possible is a single metal forming a structure between two bases that's crossing through two different strands, and that's referred to as an interstrand. So intra is the same strand, inter between two different strands. But there's also more there. It's not just that that's possible. Also, you have the possibility of a metal binding to the phosphate backbone. Okay, and sometimes even through just binding to the backbone, you have a metal capable of linking the DNA or RNA to other biomolecules. So here's just a representation of it, coordinated to the actual DNA in this case, but also facilitating a protein binding. Okay? So that's something that metals are capable of doing. But to the right side, in B, we have another layer of binding interaction. And that layer is of drugs, and we are aware of this, how drugs can intercalate between the base layers, right? Well, just imagine that you have a metal compound that has planarity, has aromaticity to enable the metal compound to intercalate into the base layer. There's also another way in which metal compounds, that wouldn't be the individual ions, that would be an actual compound that's facilitating this interaction. Okay? So these are different ways in which metals can interfere with DNA, and this to an extent is what people can exploit, let's say for an anti-cancer application, if you want to disrupt DNA, which is principal for the application, by trying to coordinate and disrupt the actual structure, and probably even trying to break. All right, so I'm going to leave you right there, and I just want to see, are there any questions? Anyone from online or anyone here? Yeah, go ahead. Mhm. Yeah, right. So it's going to matter, right? So the example they gave you was albumin. So it turns out with that particular protein, the N-terminus actually has a really unstructured part. So it's basically kind of like this N that's kind of flopping there, that it has the first three amino acids of what participates. So the amino group, and then the subsequent two amino acids will form a square plane arranged around copper or nickel. That's actually referred to as, in that protein, let me write it down, as a common group has an acetone site. So that is the amino terminus, copper, and nickel binding site. So because of that being accessible to the metal, that's what's capability. So it does matter, like the accessibility. Can an actual metal reach it at that point, whether it's going to enable coordination to take place? Other questions? Sorry, yes. Yeah, it's just where they're located. So you see here, amino number 13, 15, 29 is the location. So that beta domain is that part that coordinates the fashion. The alpha domain are those amino acids. So that's just like the classical signature of what part of the protein coordinates and how many things. So yeah, those numbers are coming from the primary sequence of it. Other questions? Anyone, virtual, any questions?
No.
Okay, all right, well, that's basically it for now, so we'll continue our discussion in the next lecture, with more about the coordination. All right, I'll see you all next time.